The issue you're likely referring to is inductive reactance, sometimes described as the skin effect when dealing with alternating current, or AC, in electrical systems using metal conduits like electrical metallic tubing, or EMT. When a ground wire, or any current-carrying conductor, is run through a ferromagnetic material like steel conduit, it creates a magnetic field around the conductor. This magnetic field induces a counter-electromotive force, or voltage, in the conductor opposing the flow of current. This opposition is inductive reactance measured in ohms. Firstly, let's understand how inductive reactance arises. When alternating current flows through a conductor, it generates a magnetic field that expands and collapses with the changing current. If the conductor is enclosed within a steel conduit, a portion of the magnetic field lines will be concentrated within the conduit material. This concentration of magnetic flux within the steel conduit induces a circulating current within the conduit wall. This circulating current, in turn, generates its own magnetic field that opposes the original magnetic field created by the conductor. This opposing magnetic field reduces the overall current flow in the conductor, effectively increasing the impedance of the circuit. Secondly, the skin effect contributes to this issue. At higher frequencies, alternating current tends to flow primarily on the surface of a conductor, a phenomenon known as the skin effect. In the context of a ground wire within a steel conduit, the skin effect causes a current to concentrate on the side of the conductor closest to the conduit wall. This proximity effect increases the inductive reactance because the magnetic field is more concentrated near the steel conduit. Thirdly, consider the implications for grounding. Grounding is essential for electrical safety, providing a low impedance path for fault currents to flow back to the source, tripping the circuit breaker or fuse and preventing electrical shock hazards. When inductive reactance is present in the grounding path, it impedes the flow of fault current, delaying the tripping of the overcurrent protection device and increasing the risk of electric shock. Fourthly, to mitigate inductive reactance in EMT conduit grounding, several methods can be employed. One common technique is to bond the conduit properly at both ends using bonding bushings and jumpers. Bonding ensures that the conduit itself becomes part of the grounding path, reducing the impedance and providing a more effective ground. Another method is to use aluminum conduit instead of steel. Aluminum is a non-ferrous material, meaning it does not exhibit the same magnetic properties as steel. Therefore, aluminum conduit does not concentrate the magnetic field around the conductor, minimizing inductive reactance. Fifthly, an important consideration is the National Electrical Code, or NEC, requirements for grounding and bonding. The NEC provides specific guidelines for sizing and installing grounding conductors and bonding jumpers to ensure electrical safety. Following these guidelines helps to minimize inductive reactance and ensure that the grounding system functions effectively. For example, NEC Section 250.4 A5 addresses effective ground fault current path. This section emphasizes the importance of a low impedance ground fault current path to facilitate the operation of overcurrent protection devices. Furthermore, NEC Section 250.102 covers bonding jumpers and their sizing requirements. These jumpers are crucial for connecting different metallic parts of the electrical system to create a continuous and effective grounding path. Specifically, NEC Table 250.102. Sheet 1 provides guidance on the minimum size of bonding jumpers based on the size of the ungrounded conductors. Moreover, NEC Section 300.3 addresses the installation of conductors in the same raceway. This section requires that all circuit conductors, including the grounding conductor, be installed together in the same raceway to minimize impedance and ensure effective fault current return. Sixthly, the type of grounding conductor is important. Using a grounding conductor with a larger cross-sectional area reduces its resistance and inductive reactance. Copper conductors are generally preferred for grounding due to their low resistance and high conductivity. However, aluminum conductors can also be used if they are properly sized and installed. Seventhly, consider the length of the conduit run. Longer conduit runs tend to have higher inductive reactance due to the increased length of the magnetic field interaction. Therefore, it is important to minimize the length of the conduit run whenever possible. In situations where long conduit runs are unavoidable, additional bonding jumpers may be required to reduce the overall impedance of the grounding path. Eighthly, using a separate equipment grounding conductor or EC run outside the conduit can also help reduce inductive reactance. This method involves running a bare or insulated copper wire alongside the conduit and bonding it to the equipment grounding terminals at both ends. The separate EGC provides a low impedance path for fault current, bypassing the inductive reactance of the conduit. Ninthly, understanding the role of grounding electrodes is essential. Grounding electrodes such as ground rods, ground plates, and underground metallic water pipes provide a connection to the earth, which serves as a reference point for electrical potential. These electrodes help to stabilize the voltage and provide a path for dissipating ground faults. The NEC specifies requirements for the type, size, and installation of grounding electrodes to ensure effective grounding. Tenthly, regular inspection and testing of the grounding system is important to ensure its continued effectiveness. Grounding systems can degrade over time due to corrosion, loose connections, or physical damage. Regular inspection helps to identify and correct any problems before they become a safety hazard. Testing the grounding system involves measuring the impedance of the grounding path to verify that it is within acceptable limits. Finally, always consult with a qualified electrician to ensure that your electrical system is properly grounded and bonded. Electrical work can be dangerous, and it is important to follow all applicable codes and regulations. A qualified electrician has the knowledge, skills, and experience to design, install, and maintain a safe and effective grounding system. In summary, inductive reactance is a phenomenon that can occur when running a ground wire through a steel conduit, impeding the flow of fault current and increasing the risk of electric shock. By understanding the causes of inductive reactance and implementing appropriate mitigation techniques such as proper bonding, using aluminum conduit, and following NEC guidelines, you can ensure a safe and effective grounding system.